In this video, we will discuss angle measures and segment lengths formed by secants, chords, and tangents in circles. First, let's discuss what a secant line is. A secant is a line that intersects a circle in two places, or 2 points. So for example, these 2 points cross a circle, making this a secant. You also could have AB as a secant ray, because if we start at A and continue through B, it crosses the circle in 2 places, making an example of a secant. Additionally, you also could have segment AB, where we start at A and continue to B, is another example of a secant because it crosses the circle in 2 places as well. Now, the angles formed by secants, chords, and tangents, intercepted arcs on circles, and the measures of the intercepted arcs help us define the measures of the angles, as we will see in this video. Now, first, let's generally discuss the theorems associated, and then I'll create a summary of a chart that you can copy down in your notes. So the first theorem says that the measure formed by 2 lines that intersect inside the circle is half the sum of the intercepted arcs. Because if we look at this diagram, we have the 2 lines that intersect inside the circle, giving us this angle, which is congruent to this angle as well. However, we're only going to focus on one of them, so let's just focus on angle 1. But beyond that, we can use the 2 intercepted arcs that are formed by the crossing of those lines. So I have my first arc, which is measure of x, and the second arc, which has a measure of y. Now, if I were to summarize this, essentially what you can say is that the angle equals 1/2 times the arc plus the arc, or you could summarize this as the angle equals 1/2 times the sum of the arcs. Now, the second theorem says that if the 2 lines intersect outside the circle, it's half the difference of the measures of the intercepted arc. So if we look at this, we have the angle, we have angle 1 in all 3 cases, which intersects outside of the circle. Then we have the value of x, which in all these cases is the arc that's further away from the angle and ends up being the bigger arc, minus the value of y, which is the arc that's closer to the angle and ends up being the smaller arc in all these cases. Now, this allows us to rewrite our formula so that we have the angle equals 1/2 times x, which is the big arc, minus the small arc. So, in summary, what we have is 3 different scenarios. The first one is when the intersect of the lines are inside the circle. When the lines intersect inside the circle, as shown in the first diagram, the measure of the angle in each of these cases is 1/2 times the sum of the arcs. So I have one arc as x for both cases, plus my second arc of y. So it's 1/2 times the sum. The next one is what we talked about in our last video, where the lines intersect on the circle. And this is like we're talking about inscribed angles. And when we have inscribed angles, the angles vertex is on the circle, and we know that it's always set up so that the measure of the angle equals 1/2 times the measure of the arc. So whichever of these relationships we have, it's always 1/2 times just that intercepted arc of x. In the last example, or the last type we have, is when they intersect outside the circle, which is shown in all these diagrams. So in each of these, the lines intersect outside the circle, so that the measure of angle 1 is always equal to 1/2 times the difference of the big arc, which is always x, and that's the arc that's further away. So it's the big arc minus the smaller arc, which is closer, which in this case is always represented by y. And I would highly recommend either taking a picture of this, copying it down in your notes, or something like that, because this is going to be the key concept for this entire section. Now in this first example, it's asking for this angle x right here. And if we look, these angles intercept inside the circle. So the formula that we use is that the angle equals 1/2 times the arc plus the other arc. Now if I highlight the sides of my angles to help me pick out the arcs and go all the way across the circle, I can say that my angle of x equals 1/2 times one of the intercepted arcs is this 46 on the left side of the circle. So I can fill in a 46 plus the other intercepted arc is the 90 on the other side of the circle. So I can fill in a 90. Now if I plug this in the calculator, the 46 plus 90 gives you that x equals 1/2 times 136. And then when you multiply by a half, it gives you that x equals 68. So your answer is 68 degrees. Now the next example asks you to find the value of y. And if we look, we have our angle intersects outside the circle, and we can highlight the sides of the angle. Now the formula for the outside of the circle is that the angle equals 1/2 times the big arc minus the small arc. So if I were to use this, my angle of y equals 1/2 times the bigger of the intercepted arcs that's further away is this 110. So it equals 110 minus the smaller of the intercepted arcs, which is the closer arc, which is 30. So I can fill in a 30. Now if I simplify this, this becomes y equals 1/2 times 110 minus 30, which gives us a value of 80. And when you plug it in the calculator, it gives you y equals 40. So the measure of the angle is 40 degrees. Now for the next example, it asks us to find the value of z. Now we can see from looking at this that the lines intersect outside the circle. to make the 20-degree angle, and I can highlight the sides of the angle. Now the formula we use is that the angle equals 1/2 times the big arc minus the small arc. So if I were to use this, my angle is 20, which is given. So I have 20 equals 1/2 times the big arc is the arc that's further away, which we can identify as this arc on the top left, which is 95. So it's 95 minus the small arc, which is the closer arc, which is the value of z. Now, if you want to solve this type of problem, you're going to have to solve like you're solving an equation. Now, the first thing you want to do is get rid of the fraction. So if you multiply both sides by 2, this 2 cancels with the 1/2, and 2 times 20 gives you 40. This becomes 40 equals 95 minus z. Subtract 95 from both sides. So it gives you negative 55 equals negative z. And if you finish solving, that'll give you that z equals a value of positive 55 degrees. For the next example, we can identify that the lines intersect inside the circle for the 94-degree angle. So it's inside, and the formula we use is that the angle equals 1/2 times the arc plus the arc. So if I'm identifying, I have my angle of 94. So it's 94 equals 1/2 times, and we can highlight over the sides of the angle to help us identify the intercepted arcs going all the way across the figure. So one of the arcs I'm dealing with is this arc on the left, which is given a value of x, so it's an unknown. So it's x plus the other intercepted arc has a value that's given of 112. So x plus 112. Now, in order to solve this sort of problem, we have to solve an equation. The first thing you want to do, though, is clear the fraction. So you're going to multiply everything on both sides by 2. When you do that, this 2 cancels with the 1/2. 2 times 94 gives you a value of 188 equals x plus 112. And when you finish solving, it gives you a value that 76 equals x. Now, the last example says an advertising agency wants a frontal photo of a flying saucer ride at an amusement park. The photographer stands at the vertex of the angle formed by the tangents to the flying saucer. What is the measure of the arc that will be in the photograph? Now, if I look at what's given, we can identify that the angle is outside the circle and it has a measure of 72. Now, knowing what we have learned, we know that when it's outside, it's the angle equals 1/2 times the big arc minus the small arc. Now, using the formula, we can highlight the sides of the angle, and if I highlight what my big arc is, we can see what it is. We don't know anything about it. So let's call the big arc x. So it becomes that the angle of 72 equals 1/2 times x minus the small arc. Now the small arc is shown right here. However, we don't know anything about the small arc. But what we do know is that all the arcs in a circle add to 360. So if I said that I had x plus the small arc were equal to 360, I could solve for x by subtracting x from both sides. And that would give you that the small arc equals 360 minus x. So I can represent this small arc by 360 minus x. So it's minus 360 minus x. Now, in order to solve, you first want to multiply both sides by 2 to clear the fraction. So this 2 cancels with the 1/2. 2 times 72 gives us a value of 144 equals x minus 360 minus x. Now, in order to solve this, we have a minus 360 minus x, which really means that there's a value of a 1 in front of the 360. So if you were to distribute the minus 1, it will become 144 equals x minus 360. And then you distribute the negative 1 again to the x. So negative 1 times negative x becomes plus x. Now if I simplify, I get 144 equals 2x minus 360. And now we're just solving like we normally would. So 144 plus 360 gives us 504 equals 2x. And if you divide both sides by 2, you get 252 degrees equals x. Now, if we're plugging this back in, it means that this part of the circle is valued 252, and the other half is 360 minus 252. So 360 minus 252 gives us a value of 108. So this length over here is 108. Now the question says which measure of the arc is going to be in the photograph. The measure that's going to be included in the photograph is this part down here. So this means that our final answer should be this 108 degrees.